So let us now talk about the remaining properties of the elementary signals. In fact, the ramp, the step, and the impulse signals. Precisely, we shall be talking about the relation that exists between these three signals. So, a relation that exists between the step and the pulse signal is that if we differentiate the step signal ut, so what we get is the impulse signal delta t. In other words, we can say that if we integrate the signal delta t from minus infinity to t of delta t, then this is equal to ut. Likewise, when we differentiate the expression of the ramp signal, so if we differentiate d by dt, if we take d by dt of rt, then this is equal to the step signal ut. Or we can say that if we are going to integrate the unit step signal from minus infinity to t, then what we get is the ramp signal rt. So now, using these basic properties associated with the elementary signal, we will try to draw some more waveforms, and let us start with a waveform and try to understand that how things like this are dealt with. So let me start with example 1. So let's suppose that we have the waveform. So the example is to express the given waveform mathematically and sketch d by dt of xt. So the xt, the waveform, is given as, let me draw it here, it's given as xt versus t, and this is a line that starts at 0, 1, 2 and has a magnitude of 2 at t equal to 2, and then on the negative side we have this as -1, -2, -3 and -4. So at -4 we have a magnitude 3, 4. So this is 1 is here, 2, 3, 4. So this is the waveform for xt, and we are required to find its mathematical expression first, and then we'll be sketching the waveform for d by dt, or derivative of this waveform. So there are two ways to obtain the sketch for the derivative of the given waveform. One is that can be done mathematically, and the second is we can do it directly by looking at the waveform. So let us first try to obtain the mathematical expression of it, and then we'll obtain the derivative of the mathematical expression. Then we'll later learn how to draw directly the derivative of the given waveform. So this waveform can mathematically be expressed using the ideas of the sketching that we have learned in the previous lecture. So this can be expressed, and I'm not going to explain in much detail about how are we going to obtain the mathematical expression of the waveform, because the explanation of this has already been discussed in the previous lecture. So if you still feel any doubt or have any problem in how to obtain the expression of xt for this particular waveform, you can ask me or post on the Google Classroom. You can post it privately if you feel shy, or you can email me as well. So the expression for xt can be written as, if you look into the waveform, so if you somehow have learned about how to obtain the expressions directly, so you have in fact a transition from 0 to 4, then a ramp that goes downward. So one thing is that we are going to have a unit step signal at that particular point having a magnitude of 4, and it will be starting at t equal to -4. So this can be written as 4t plus 4, and then we have a ramp signal that goes down from that point at t equal to -4, and that has a slope of -1. So the slope of this line is -1. This can be written as minus of rt plus 4. So this will be starting at point t equal to -4. So things are out of focus. Minus rt plus 4. And then now we have a positive slope, so which means that this negative slope, which could have been eliminated by a similar positive slope, and the similar positive slope. So if we further draw a positive slope starting at t equal to 0, that positive slope having this slope value same as that of this negative one will result in a 0 slope. But at this point we have in the waveform of xt a positive slope, which means that we are going to have we will have to draw beyond t equal to 0 a slope that should be 2 times the slope of this particular negative slope. So then only then we are going to get a line that will be having a positive slope, which means that we will be adding 2 times rt, which is nothing but a line that has a slope of 2, since this slope is the slope of this line is 1. And again we have to terminate this at t equal to +2. So this is going to be possible if we have another negative slope and along with a step signal that has a magnitude of -2. So if we add a negative slope minus rt -2, so this will be starting at t equal to 2, and then again we have to add another signal minus t ut -2, which starts at t equal to 2. So this is the required mathematical expression of the given waveform. And again, in order to sketch the derivative of this particular function xt, so we'll first try to write this, obtain the mathematical expression of the derivative of xt. So d by dt of xt can be written as, so 4 times of d by dt of ut is delta t plus 4 and minus d by dt of r is u t plus 4 and plus d by dt of rt is ut minus u t minus 2 minus 2 delta t minus 2. So we now will be drawing each of these components separately. So let me draw this here. We have a space. T, and so 4 delta t plus 4 is impulse that has a magnitude of 4 and will be realized at point t at time t equal to -4. So -1, -2, -3, -4. So this is going to have a slope of 4, or simply not slope, magnitude of 4. Then the next is a step signal that has negative magnitude of -1, and it starts at t equal to -4. So it will be starting at t equal to -4 and having a magnitude of -1. And this sure will go to infinity at the positive side, but we have more values. So 2 times of ut will be having a magnitude of +2 starting at t equal to 0. So it should start at t equal to 0 and will be having a magnitude of +2, but since we have -1 here, so -1 and this +2 will be +1. So this line will start at this place at 1, not 2, because this is -1, this is +2, so the net value that we get is +1. And then after beyond t equal to 2, we have these two expressions that come into picture, because before t equal to 2, these two expressions will be 0. So beyond t equal to 2, we have -ut-2, which has a magnitude of -1 and will be starting at t equal to 2, and the next is -2 delta t -2, which again starts at t, in fact which exists at t equal to 2. So this is not a continuous representation of magnitude, it's simply an impulse signal, so that is why we should not be calling it as a start. So this exists at t equal to 2 and will be having a magnitude of -2. So then this is a slope of -1. So +1, which goes to till t infinite, will be added to -1 and will be resulting in 0. But at t equal to 2, we have an impulse with magnitude -2. So this is the required waveform of the derivative of this particular waveform. Now in order to obtain the direct sketch of this waveform without obtaining the mathematical expression can be done by simply looking into the figure. So if you look into this figure, we have the first transition from 0 to +4. So derivative of this transition, which takes place within no time, will lead to an infinite, which is nothing but an impulse having magnitude of 4, which is represented here. And again, if you move further, we see that after t -4, between -4 and 0, we have a slope we have a line which has a slope of -1. So if we take the derivative of this line, we get a value of -1. So because d by dt of t is 1, or d by dt of -t is -1, so that is why d by dt of this is the ramp signal, and the slope is -1, so its derivative will be simply -1, and that is why we have represented a magnitude of -1 between -4 and 0. Now if we talk about the point, so of course we will not be talking about the point of discontinuities or the point of places where the derivative is not possible, like the knees here, and here, but we will be talking about the place where the derivative is possible. For example, between t equal to 0 and 2, or 0 and -4, or at 2. So between 0 and 2, we have a positive slope of 1. So which means that if we take derivative of this line between t 0 and 2, we will be getting a constant of +1, which is shown here. Likewise, we again have a transition from 2 to 0 at t equal to 2, which means that we are going to get an impulse having negative magnitude of -2, which is shown here. So in this manner, we can directly express a waveform, its derivative, if we know the basic representation of the derivative of the slopes or the impulses or transitions. So let us now try to do another example. So the next example is to obtain the integration of the given waveform. So let us suppose that we are given a waveform xt versus t as shown in this figure, having a magnitude 1, 1, 2, 3, and this is -1, and the impulse of magnitude 1. So suppose that we have xt represented as follows. Now we are required to obtain its mathematical representation as well as a sketch minus infinity to t of xt dt. So we are required to sketch this waveform. So we'll first try to again represent this xt in terms of the mathematical terms. So starting at t equal to 0, we have the first term which has magnitude 1, which corresponds to ut, and it ends at t equal to 1. And beyond t equal to 1 we don't have magnitude 0, rather -1, which means that we'll be adding another step signal having magnitude -2 and starting at t equal to 1. Then this goes till t equal to 3, where we again have the magnitude turning to 0, which means that we'll be adding step signal that starts at t equal to 3. And at t equal to 3, beyond t equal to 3 to infinity, the magnitude will be 0, but at the moment when t is equal to 3, we have an impulse of magnitude 1, which means that we again have to add another signal that is starting at that exists at t equal to 3 having impulse. So this is delta t minus 3. Since the magnitude of this impulse is 1, so we have taken this simply as delta t minus 3 and have not multiplied any constant with it. So this is the required mathematical expression. Now if we take the derivative of this term xt, so derivative of ut comes out to be rt. The derivative of ut minus 1 can be written as rt minus 1. The derivative of ut minus 3 can be written as rt minus 3, and the derivative of delta t minus 3 can be written as ut minus 3. So now again, in the same way that we did in our previous problem, you can express the you can draw the waveform for the integration of xt using this mathematical expression, or you can draw the waveform directly by looking at the sketch of the original xt. So let us try to draw this mathematically first, then we'll try to correlate the mathematically drawn waveform with the waveform of xt. So we have xt with a slope of rt, and this will start at t equal to 0, and will, let's say, this goes to till t equal to 1, because at t equal to 1 we have another expression. So we'll be drawing this bit between 0 and t equal to 1, and then at t equal to 1 we have a sudden drop, which can be expressed. So this will be having a slope of 1, and this will be having a slope of -2. So after t equal to 1, between 0 and 1 we have this rt, and this thing starts at t equal to 1, so which means that we are going to have the slope minus this slope. So this is twice the slope of rt, and that is why we are going to get a line with slope -1. So this is 1, this will be ending at 2, and will be going beyond to t equal to 3. At t equal to 3 we have another positive slope, So the slope of this line is -1, and if we are going to add another slope of +1, then we are going to get a line with 0 slope. So this should be drawn straight, but and we have an step signal that also starts at t equal to 3 and is having a unit magnitude. So at this point the magnitude is -1, and if we add the slope rt -3 here, the line should be straight having magnitude -1, but since we have another step signal that starts at t equal to 3 having a positive magnitude of 1, and that is why we will be having this type of waveform. So this is the required representation of the given waveform. Now this can also be correlated with the waveform. If you look between time 0 and 1, we have the straight line. So if you integrate the straight line, what you get is a ramp like this, and again a transition. This transition will lead to no effect if integrated. Then further a straight line integration leads to a negative slope like this. Then again the transition, and again we have a impulse of unit magnitude, which if integrated will result to a step value. So that again is going to be represented as at this particular point we will be having. So if you integrate this line which exists for no duration of time, this particular transition, then the integration would lead to 0. So likewise we have many more questions that can be done based on the derivative of the waveform. So I give one more question as home assignment to you. This will be probably home assignment number 3 or 4. So I leave this to check whether this is 3rd or 4th. So I'll draw the waveform that you will be submitting as home assignment. So suppose that we have the waveform of, let's say this is the voltage waveform, Vt. So this is -1, the magnitude is -2, and then we have, let's say, the slope, the same slope here, and this is 1, this will be 2, a straight line till 2, then a sudden change to 3, and from this 3 we have a drop till 1 at 4. So this is t equal to 3, this is 4. Then between 4 and 5 a straight line, and then we have 6, 7, a slope, a negative slope, and then again a 0. So you are required to submit this as a home assignment. So this is your home assignment, question number 3 probably. Now we move on towards the remaining classification of the signals. Let's get up this. So based on the features that we if you remember that we have already classified, we already discussed about the classifications of the continuous time and discrete time signals as well, and these were the 5 classifications where we normally or broadly classify signals into, and this were discussed, I think, if I remember correctly. And then I talked about the continuous and discrete time representation of the signal. Then we talked about the discrete representation of the elementary signal, the unit step, unit ramp, unit impulse, the sinusoid and exponential signals, and we did this question as well. So this was already done in our previous lectures, and this was given as home assignment. Okay, now we shall be talking about the even and odd representation of the signals. So let me break the lecture here, and we'll be continuing this part in the next lecture. So this could be easy for you to perceive.